Hi, welcome back. So in the previous video, I discussed how to compute the line integral over a generic curve. In this video, I'm just going to briefly discuss this slight upgrade, you could say. So here, we're going to integrate function f over c, and we're going to change with respect to x. We're only changing with respect to x, so that's why I wrote dx. And we get this equation, right? So it's integral of f, again, xt and yt are x and y as it's related to the function, as it's related to the curve c. So why do I get this right here instead of the full square root of x over t plus y over t squared and all that? Well, let me explain. So I had previously dx dt squared plus dy over dt squared, right? dt at the end, right? dt. I'll put that dt. Okay, now when I write dx, I said you're only changing with respect to x, right? So if you're not changing as t changes, you're only changing with respect to x. That's what dx means. So change on the curve, but only in x, right? So what would this mean? Well, it means that this is going to go to 0, right? This is 0, right? Because if y is not changing, it's 0, okay? So I'm going to erase this, right? And put that dt back, okay? So, look, I have a square and a square root. So, square and square root, those cancel. So it's just going to be dx dt, dt, right? And this dx dt, that's just this right here, right? That's what the prime is. So don't let the symbols scare you. Nothing scary here. There's just derivative with respect to x. Derivative of x with respect to t. This is very simple. So you have a curve, and it's going to have x components, and it's going to have y components. And we claim that we're only going to move with respect to x, right? If we're only moving with respect to x, take a derivative of your curve with respect to x. Take the x component, take its derivative with respect to t, ignore the y. Plug it into this equation on the right, and do your calculations. Okay, so in the next video, we'll actually do some calculations. This was just to give you the basics.